السلام عليكم ورحمة الله وبركاته. Miro Nasroor, chemistry teacher. Our topic today, organic isomers. Isomers. They are different compounds with the same molecular formula, but they are different in the way the atoms are connected to each other. So, isomers are different in physical or chemical properties. This phenomena is isomerism. The types of isomerism. Number 1, structural isomerism. Number 2, stereoisomerism. The first type is structural isomerism. Types of structural isomerism. Structural isomerism is divided into 4 types: chain isomerism, functional isomerism, position isomerism, and metamerism. Structural isomerism, in which the molecules of isomers have the same molecular formula but a different bonding arrangement among the atoms. Structural isomers have different IUPAC name, the same or different functional groups, different physical properties, so they can separate by physical techniques such as distillation. Different chemical properties, they behave differently or give different products in chemical reaction. The first type of structural isomerism is a chain isomerism. Chain isomerism have the same molecular formula but differ in the order in which the carbon atoms are bonded to each other. Example: N-butane and isobutane. In front of you, 2 molecules. The first one contains 4 carbon atoms. The second one contains the same number of carbon atoms, but the bonding or the arrangement of a carbon atom is different. Position isomerism. Position isomer have the same molecular formula but differ in the position of a functional group on the carbon chain. Example of position isomerism is 1 propabutane and 2 propabutane. In front of you, the 2 molecules, each of them contains 4 carbon atoms. The first one connected with bromine atom as a terminal atom, but in the second molecule, the bromine connected with the second carbon atom. The second example, ortho-dichlorobenzene and meta-dichlorobenzene. In this molecule, the second chlorine atom is connected in ortho position. In this molecule, the chlorine atom is connected in meta position. Functional isomerism. Functional isomers have the same molecular formula but different functional group. For example, ethyl acetoacetate in an equilibrium mixture of 2 forms. One is ketone form and the other is enol form. At room temperature, the mixture contains 93% of ketone form and 60% of the enol form. In front of you, the 2 isomers, ketone form and enol form. Metamerism. This type of isomerism is due to the unequal distribution of carbon atom on either sides of the functional group. As example, diethyl ether and methyl propyl ether. The distribution of carbon atom around the oxygen atom is different in each molecules. Number 2, stereoisomerism. The stereoisomers have the same structural formula but differ in arrangement of atoms or groups in the space. Types of stereoisomerism: geometrical isomerism, optical isomerism. Geometrical isomerism. This type of isomerism is due to the restriction in rotation about double bond or about single bond in cyclic compound. In alkenes, recall that the carbon-carbon double bond consists of a sigma and pi bonds. The sigma bond is formed by the head-by-head overlap between 2 sp2 hybrid orbitals. The pi bond is formed by side-by-side overlap between 2 sp2 hybrid orbitals. So the pi bond locks the molecule in one position. As example, ethylene C2H4. This is the sigma bond formed by head overlap between sp2 orbitals, or overlap between sp2 orbital and the hydrogen orbital. This is the pi bond, side by side overlap between two sp2 orbitals, hybrid orbitals. This is the two bonds with each other. Geometrical isomerism. The two carbon of the double bond and the four atoms that are attached to them lie in one plane, and their position in space are fixed. Therefore, rotation around the double bond is not possible, because rotation would break the pi bond. So, the restriction of rotation about carbon-carbon double bond is responsible for the geometrical isomerism in alkanes. Rotation around CC double bond does not occur, but bond rotation can occur in sigma bond. Example, 2-butane. It exists in two special arrangements, cis-2-butane and trans-2-butane. The cis isomer is a molecule in which the two similar groups are on the same side of the double bond, the same side. The trans isomer is a molecule in which the two similar groups are on the opposite side of the double bond, opposite side of the double bond. The cis isomer can change to trans isomer by heating to a high temperature or absorbing light. The heat energy breaks the pi bond so that rotation of sigma bond becomes possible. On cooling, the reformation of pi bond can take place in two ways, giving a mixture of the two isomers. Heating can break the pi bond and rotation can take place. After reformation of the pi bond, we can see cis and trans isomers. The cis and trans isomers different in physical properties such as melting point and dipole moment. The trans isomer has no dipole moment because it is symmetrical. The cis isomer is polar and have strong intermolecular force between the molecules, so the cis is stronger than the trans isomer. Example, butanoic acid. In trans isomer, melting point 130 degrees Celsius and trans form has 288 degrees Celsius. So there is a big difference in physical properties as melting point between the cis and the trans isomers. In cyclic compounds, the rotation is not possible about carbon-carbon single bond, forming the ring, because rotation would break the bonds and breaks the ring. This is the example, cis 1,2-dimethyl cyclopropane, trans 1,2-dimethyl cyclopropane. In cis isomer, the two methyl group in the same direction. In trans isomer, the two methyl group in opposite direction. In cis 1,2-dimethyl cyclopropane, the two methyl group are on the same side of the ring, In trans 1,2-dimethyl cyclopropane, the two methyl group are in opposite side methyl group and the other methyl group. P. Optical isomerism. Optical isomerism are two compound molecules which have the same molecular formula and structure formula, but one can't be superimposed on the other. Example, lactic acid has two not identical structure because they can't be superimposed on each other. Optical isomerism can occur when there is a symmetric carbon atom. Asymmetric carbon atom, chiral atom, is a carbon atom that is attached to four different types of atoms or groups of atoms. The enantiomers They are optical isomers, differing only in the three-dimensional arrangement of substituent. What is the difference between chiral and achiral molecules? Chiral molecules are non-superimposable with their mirror image. Achiral molecules are superimposable with their mirror image. Most pairs of enantiomers have identical physical properties that do not depend on the structure, as boiling point, melting point, solubility, refraction index, and many other properties. Enantiomers differ in only one physical property, which is the interaction with plane polarized light. The plane of plane polarized light is rotated when the light passes through a solution of an enantiomer. This property of chiral compounds is called optical activity. The rotation is called optical rotation. Optical activity. It is the phenomenon in which chiral molecules rotate polarized light in either a clockwise or anti-clockwise direction, due to the interaction between light and the individual molecules through which it passes. Optical isomers can rotate the plane of plane polarized light when a solution is viewed from above. The negative enantiomers rotate the plane anti-clockwise to the left. The positive enantiomer rotates the plane clockwise to the right. A mixture containing equal concentration of the positive and negative enantiomer is not optically active. It will not rotate the plane of polarization. Racemic mixture or racemate. A mixture that containing equal concentration of positive and negative enantiomer and optically not active and can't rotate the plane of polarization. Lactic acid has three structures. Two are optically active and the third is optically inactive. Optically active, optically active, optically inactive. Melting point 26 degrees Celsius, melting point 26 degrees Celsius, melting point 80 degrees Celsius. Why? The optical isomers rotate the plane of polarized light. As moving, charged particles, the electron in a molecule produces electromagnetic field, which interact with the electromagnetic field of light. This interaction indirectly rotates the plane of the polarized light by a small amount. The direction and the quantity of this small rotation depend on the orientation of the molecule in the solution. Reference. Thank you and goodbye.